morning, everybody. I welcome you all to my second lecture on network synthesis. In my previous lecture, I have discussed regarding the introduction of network synthesis and various methods in detailed procedure how to synthesize a given impedance function using both Foster as well as Core forms. In today's lecture, we shall see the detailed procedure of how to synthesize a given impedance function of RL category. So let us consider an example of an impedance function s plus 1 into s plus 3 divided by s plus 2 into s plus 4. So before we go to synthesize this given function, there are few basic things that you should know before proceeding to synthesizing any given function. If the given function is an impedance function, then inductor will be in the form of Ls, capacitor will be in the form of 1 by Cs, and resistor will be in the form of R. Then if the given function is an admittance function, then inductor will be in the form of 1 by Ls, capacitor will be in the form of Cs, and the constant term that you get will be conductance, that is G. Foster first form and second form both utilizes partial fraction method, whereas Core first and second form utilizes continued fraction method. An impedance RL function is same as an admittance RC function. Similarly, an impedance RC function is same as the admittance RL function. So before going to synthesizing this given impedance function, first we should know what are the poles and zeros of this given function. If you do not have any idea about poles and zeros, the values of s for which the numerator of this function becomes 0 are called zeros, and the values of s for which the denominator of this function becomes 0 are called poles. So from this function we can see that for s is equal to -2 and -4, the denominator of this function becomes 0. So these are called poles. And when s is equal to -1 and -3, the numerator of this function becomes 0. So these are called zeros. So the first step before synthesizing any given function is to draw a pole zero plot. So if this is your j omega axis, this is the negative real axis, this is the positive real axis, this is the origin. So poles are denoted by cross and zeros are denoted by 0. So if the scale is -1, -2, -3, -4, so we have poles at -2 and -4. So at -2 and at -4 we have poles, and at -1 and -3 we have zeros. So after drawing pole zero plot, so first we have to identify whether this given function belongs to RL or RC or LC. So that is the first objective of our solving this problem. So that can be obtained by drawing pole zero plot. So we can see by drawing pole zero plot, near the origin, as you can see, we have a 0. So near origin, if we have a 0, then this is referred to as an RL function. So after drawing pole zero plot, we should identify whether it is an RL function, an RC function, or an LC function. So the given function will belong to an RL function if you have a 0 near the origin. The given function belongs to an RC function if we have a pole near origin, and the given function belongs to an LC function if all the poles and zeros will lie only on j omega axis. So in this way we can identify whether the given function belongs to an RL function, RC function, or LC function. So now we know that the given function belongs to an RL function. So we shall proceed with how to synthesize the given impedance function in all the 4 methods. The first method is Foster first form. So the procedure is, as we know, the Foster first form should be applied only to an impedance function. So if an admittance function is given, that we should convert it into an impedance function. First we should check whether the numerator degree is less than the denominator degree. If it is true, then we should apply partial fractions. If the numerator degree is greater than or equal to the denominator degree, then we should divide numerator by denominator once. If the remainder is positive, we have to apply partial fractions. If the remainder is negative, we should consider z of s by s and then apply partial fractions. So first let us see. So the given function here is given in impedance function. So there is no need to convert. Now we should check the numerator degree and denominator degree. Here you can see the numerator degree is 2, the denominator degree is 2. So numerator degree is equal to the denominator degree. So if the numerator degree is equal to denominator degree, we should divide numerator by denominator once. So first, if we multiply all these, the numerator becomes s square plus 4s plus 3. Then the denominator becomes s square plus 6s plus 8. So since the numerator degree is equal to the denominator degree, I am dividing numerator by denominator once. So s square plus 6s plus 8, s square plus 4s plus 3. So this goes once. So you'll get s square plus 6s plus 8. So upon dividing, as you can see, first term will cancel and the remainder is minus 2s minus 5. So here we can see the remainder is negative. So if the remainder is negative, we should consider z of s by s, which is nothing but s plus 1 into s plus 3 divided by s into s plus 2 into s plus 4. So after considering z of s by s, we apply partial fractions. This can be written as a by s plus b by s plus 2 plus c by s plus 4. As you know, a is nothing but it is s plus 1 into s plus 3 divided by s plus 2 into s plus 4, and substitute s is equal to 0. So after substituting, you will get a is equal to 3 by 8. So if I want b value, so it is nothing but s plus 1 into s plus 3 divided by s into s plus 4. Since except this term, you have to consider remaining terms and substitute s is equal to minus 2. So we will get b is equal to 1 by 4. Similarly, c value, except this term, consider the remaining terms. So C is equal to S plus 1 into S plus 3 divided by S into S plus 2, and substitute S is equal to minus 4. So C value you will get 3 by 8. So the shortcut way of finding all the constant terms. So for finding constant A, except S, consider remaining terms and substitute S is equal to 0. For B, except S plus 2, consider the remaining terms and substitute S is equal to minus 2. And for C, except S plus 4, consider remaining terms and substitute S is equal to minus 4. So we have obtained A, B, C values. So now we can write the given function z of S by S as, so A value I got 3 by 8 by S. B value I have got 1 by 4, so 1 by 4 by S plus 2, and C value I have got 3 by 8 S plus 4. So from this I can write Z of S is equal to 3 by 8 plus 1 by 4 or S by 4 by S plus 2 plus 3S by 8 divided by S plus 4. So this we can see it is in the form of Z of S is equal to Z1 of S plus Z2 of S plus Z3 of S. So this is a constant term. So this indicates the resistor value is 3 by 8 ohms. So we have got the first element of our network. So as I told you, the obtained terms after applying partial fractions must be either in the form of R or Ls or 1 by Cs. But as you can see, the second and third terms are neither in the form of R or Ls or 1 by Cs. So it means that these two terms are parallel combination of R and L. So how we can segregate what is the value of R and what is the value of L in each of the terms. So let us consider the second term, that is Z2 of S is equal to S by 4 divided by S plus 2. So always ensure that the numerator is made 1 so that we can represent Z2 as 1 by Y2. So this I can write as 1 divided by 4 by S into S plus 2. So this is nothing but 1 by 4 plus 8 by S. So this Z2 I can write as 4 plus 8 by S, which is nothing but 1 by Y2 of S. So since it is admittance, the constant term represents G, and this is in the form of 1 by Ls. So if G value is 4, then obviously R2 value is 1 by 4 ohms. So this, since it is in the form of 1 by Ls, that is L1 or 1 by L1s, L1 value is nothing but 1 by 8 henries. So similarly, third term, if I consider Z3 of S is equal to 3S by 8 divided by S plus 4. So again, make the numerator as 1. So this I can write as 8 by 3S into S plus 4. So this eventually becomes 1 by 8 by 3 plus 32 by 3S. So again, this is nothing but Z3 of S is equal to, it is nothing but 1 by Y3 of S, which is 8 by 3 plus 32 by 3s. Since again here admittance constant indicates G2, and this is in the form of 1 by L2s. If G2 value is 8 by 3, then R2 value is 3 by 8, or to be precise G3 R3. Okay, so this is L2 value is 3 by 32 Henry. So we obtain all the values of Z1, Z2 and Z3. So using this partial fractions, now we will synthesize the given network. We all know that for Foster first form, Z of s can be written as Z1s plus Z2 of s plus Z3 of s. So all, since impedances are added, they are in series. Z1, Z2 and Z3. This is the general representation of an impedance function using Foster first form. So instead of Z1, we have obtained resistor 3 by 8 ohms. So instead of Z1, I will get a resistor 3 by 8 ohms. Instead of Z2, as you can see, Z2 have represented as 1 by Y2. Since Y is being added here, so you know if admittances are added, these two elements should be in parallel. So resistor 1 by 4 and inductor 1 by 8 Henry should be in parallel. But this parallel combination should be in series with Z1. So Z2 indicates the parallel combination of R and L. R value is 1 by 4 ohms and inductor value is 1 by 8 Henry. Similarly, Z3. Z3 we have indicated as 1 by Y. Since here also admittances are added, these two elements, that is resistor 3 by 8 and inductor 3 by 32 Henry, will be in parallel. But this parallel combination again should be in series with the previous impedance Z2. So here also Z3 indicates the parallel combination of Z and parallel combination of resistor and inductor, where the resistor value is 3 by 10 ohms and inductor value is 3 by 32 Henry. So lastly, the synthesis by synthesizing the given function. So this is the network that we obtain. So 3 by 8 ohms. Instead of Z2, I'll get 1 by 4 ohms. This is 1 by 8 Henries. This is 3 by 8 ohms. And this is 3 by 32 Henries. So this is how we synthesize a given function using Foster first form. Now next we shall go for Foster's second form. As we know, the Foster's second form, admittance y of s should be considered. So given function is anyhow z of s is equal to s plus 1 into s plus 3 divided by s plus 2 into s plus 4. So considering y of s, which is nothing but reciprocal of this, so it is s plus 2 into s plus 4 divided by s plus 1 into s plus 3. So The procedure here also is the same. We have to apply partial fractions but to an admittance function y of s. Here also we should check whether the numerator degree is less than the denominator degree. If it is so, we should apply partial fractions. If the given function is in impedance, then we should convert it into admittance. So if the numerator degree is greater than or equal to denominator degree, then the same procedure as we have done in the first form, you should divide numerator and denominator once and apply partial fractions if the remainder is positive, and consider y of s by s if the remainder is negative and apply partial fractions. So let us proceed with the first second form. Admittance function. Here also we can observe that both the numerator degree and the denominator degree are same. So we have to divide numerator and denominator once. So this I can write as you know s square. The numerator becomes s square plus 6s plus 8. The denominator becomes s square plus 4s plus 3. So after dividing numerator by denominator once, so x square plus 6s plus 8, so this goes once, s square plus 4s plus 3. Okay, we should multiply such that the first term gets cancelled. Okay, so s square, so this get 2s plus 5. So here you'll get remainder is positive. So since remainder is positive, this y of s I can write as, so this is the y of s. So we from this we can write the y of s as 1 plus 2s plus 5 divided by s square plus 4s plus 3. That is quotient plus remainder divided by dividend. Okay, so y of s is nothing but 1 plus 2s plus 5 divided by this. Anyhow we can segregate as s plus 1 into s plus 3. So this I can write as y1 of s plus y2 of s. So here we have got a constant value 1. So since in admittance, since we have got a constant value, this indicates g. So therefore we have got here the first element r1 is equal to 1. So the second term, let us see, y2 is nothing but 2s plus 5 by s plus 1 into s plus 3. Applying partial fractions, so this becomes a by s plus 1 plus b by s plus 3. So the same procedure, consider the entire term except s plus 1 for obtaining a value. 2s plus 5 divided by s plus 3 and substitute s is equal to minus 1. Will b is equal to, except s plus 3, remaining, consider remaining term 2s plus 5 divided by s plus 1, substitute s is equal to minus 3. So you will get a value as 3 by 2 and b value is 1 by 2. So y of s can be written as 1 plus a value I've got as 3 by 2 divided by s plus 1, and b value have got as 1 by 2, which is s plus 3. So again, since these two terms are neither in the form of, since this is an admittance function, it should be either in the form of g or in the form of 1 by ls or in the form of cs. So the second and third terms are neither in the three forms, then it means that this term is a parallel combination of r and l. This term is also a parallel combination of r and l. So as we have seen in Foster first form, in order to solve and identify the individual elements of parallel combination, we have to make the numerator as 1. So consider y2 of s, which is 3 by 2 by s plus 1. I can write it as, make the numerator as 1, 2 by 3 into s plus 1. So this is nothing but 1 by 2 into s plus 2. So this I can write as 1 by 2s plus 3 plus 2 by 3. So this is nothing but 1 by z2 of s. So since this is an impedance function and impedance terms are getting added, this is in the form of ls and this is the form of r. So since this is in the form of ls, L2 value is nothing but 2 by 3 henries and R value is nothing but 2 by 3 ohms. Similarly, Y3 is nothing but the third term that we should consider, 1 by 2 divided by s plus 3. Make the numerator as 1, so it becomes 2 into s plus 3, so 2s plus 6. This also I can write as 1 by z3. So here also impedances are getting added. So since this is an impedance term, it is in the form of ls, it is in the form of r. So L3 value is 2 henries and R3 value is 6 ohms. So now we have segregated all the two terms. So the general representation, as we know, of Foster's second form is y1, y2 and y3. Instead of y1, I've got since this is G and R1 value is nothing but 1 ohms. So instead of y1, I'll get a resistor of value 1 ohms. So instead of y2, so y2 we have represented as 1 by z. So it means since impedances are being added, these two should be in series. That means 2 by 3 Henry and 2 by 3 ohms must be in series, but this series combination must be in parallel with the previous resistor. So instead of y2, I'll get a series combination of R and L. R value is 2 by 3 ohms and inductor value 2 by 3 Henry. Even y3 we have represented as 1 by z. So this means these two are in series since impedances are being added. So R and L, R value is 6 ohms and L value is 2 henries. So you can modify the given general. Instead of y1, we have got resistor 1 ohm. Instead of y2, we have got series combination of resistor 2 by 3 ohms and an inductor 2 by 3 henries. And so y3 also we have got a series combination of R and L of 6 ohms and 2 henries. So this is the network after synthesizing the given function. So the third method is Core first form. As we know, Core first and second form uses continued fraction method. So in Core first form, So this is the given impedance function, that is s plus 1 into s plus 3 divided by s plus 2 into s plus 4. So this I can write as s square plus 4s plus 3, and this is s square plus 6s plus 8. Since both the numerator and denominator are arranged in descending powers of s, we can move forward in applying continued fraction. So s square plus 6s plus 8, s square plus 4s plus 3. So this always multiply with a term such that the first term will cancel each other. So if I multiply 1, s square plus 6s plus 8, get minus 2s minus 1. Here the remainder in the first stage itself we are getting negative. So we know the procedure that if the remainder becomes negative, we should consider y of s. So the y of s is nothing but s square plus 6s plus 8 divided by s square plus 4s plus 3. So after considering y of s, we should apply continued fraction to y of s. So s square plus 4s plus 3 plus 6s plus 8. So multiply once, you'll get 4s plus 3. So the first term will get cancelled. It's 2s plus 5. So here remainder is positive. So if the remainder is positive, we'll continue the same procedure. So the same term is carried forwarded here, that is s square plus 4s plus 3. So multiply such that the first term always becomes 0. So here I have 2s, but I want here s square. So if I multiply by s by 2, then here I will get s square, and here I will get 5 by 2. So always multiply with a term such that your first term gets cancelled. So s square. So this I will get as 3 by 2s plus 3. So here also the remainder is positive. I'll carry forward this term here, 2s plus 5. So here also I have 3 by 2s, but here I want 2s. So if I multiply by 4 by 3, here you will get 2s, here I will get 4. Here also the remainder is positive. This term is carried forwarded here. It's 3 by 2s plus 3. So here in order to cancel the first term, multiply directly by 3 by 2s 3. Here also remainder is positive. The same thing is carried forwarded here. I multiply by 1 by 3. So in this entire process, as you can see, the remainder is always positive. So after we finish applying continued fraction, so the quotients that we get, okay. So since we have done on admittance y of s, the first term is y1, and alternatively assign as impedance and admittance. So here, since we have considered y of s, the first term becomes admittance, the second one is impedance, third term is admittance, fourth term is again impedance, and the fifth term is again admittance. So it is nothing but an alternation of impedance and admittance. So since we have considered, we know that the A general representation of core first form is nothing but this ladder. So as I told you earlier, if core first and second form are done on impedance function, then this is the general representation. But if core first and second form are done on admittance y of s, then this first term will not be present. The ladder will start from y1. So in this case, the first term admittance. So admittance is a constant. So since admittance is a constant, y of s, this is nothing but indicates G. So that means the first value R1 is nothing but 1 ohm. The second term is impedance. So Z2 is equal to, I've got S by 2. So S by 2. So impedance, it is in the form of Ls. So that means L1 value or L1S. L1 value is nothing but 1 by 2 henries. The third term is 4 by 3. So Y3 is 4 by 3, which is again G. So that means R3 is nothing but 3 by 4 ohms. The fourth term is impedance again, 3 by 3s by 2. So Z3 is 3 by 2s, which is again in the form of Ls. So L3 is nothing but 3 by 2 henries. And the last term is admittance, Y3. So Y3 is nothing but 1 by 3, which is again G. So it means R3 is 3 ohms. So the ladder function. So the ladder function, as you know, general representation is y1, z2, y2, z3 and y3. So instead of y1, I have got a resistor R1. So instead of y1, I got a resistor R1 of value 1 ohms. Instead of Z2, I have got an inductor 1 by 2 henries. So instead of Z2, got an inductor of 1 by 2 henry. Instead of Y3, I got a resistor 3 by 4 ohms. So Y3, Y2, yes, 3 by 4 ohms. This is actually Y2. This is R2. So here 3 by 4 ohms. And Z3, instead of Z3, we have got an inductor 3 by 2 henries. So instead of Z3, I got 3 by 2 henries. And the last Y3, we have got a resistor 3 ohms. So Y3, I have got a resistor 3 ohms. So this is the network obtained after synthesizing the given function using core first form. The last method is core second form. The main difference between core first and second form is in core first form, we arrange both numerator and denominator in descending powers of s, whereas in core second form, we arrange both numerator and denominator in ascending powers of s. So this is the given impedance function. Z of s is equal to s plus 1 into s plus 3 by s plus 2 into s plus 4. So on multiplication we get s square plus 4s plus 3 divided by s square plus 6s plus 8. So this we have to arrange in ascending powers of s. So we can write z of s is equal to 3 plus 4s plus s square divided by 8 plus 6s plus s square. So applying continued fraction. So 8 plus 6s plus s square and 3 plus 4s plus s square. So the same concept. So on multiplying by a term, we should cancel the first term. So I have 8 here, but I want 3 here, so I multiply by 3 by 8, which will give 3. So 6 into 6 by 8, which will give 18 by 8 into s plus 3 by 8 s square. So cancel out the first term. Multiply, it will give 14 by 8s plus 5 by 8 s square. So since the remainder is positive here, write the same term 8 plus 6s plus s square. So here I have 14 by 8, but I want here 8. So in order to eliminate this term, I'll first multiply by 8 by 14s. By multiplying that, I'll get the coefficient as 1. So there, instead of that, I want here 8. So I'll multiply by 8. So we'll get 8 here. If I multiply, we'll get 320s by 112. First term will get cancelled. So this will give you 352 by 112 into s plus s square. Here also the remainder is positive, so the same term will be carried forwarded here. So 14 by 8 s plus 5 by 8 s square. So here I have 352 by 112 into s, but I want 14 by 8 into s. So in order to make that value as 1, I will multiply by 112 by 352 into the value that I want, 14 by 8. So it becomes 14 by s, and if I multiply this, it becomes 196 s square by 352. The first term will get cancelled, so you will get 24 s square by 352. Since again this is also positive, so I'll consider 24 s square by 352. So the same term we carry forwarded here, so it is 352 s by 112 plus s square. So here again I have 24 by 352, but I want 352 by 112. So you can multiply by 352 by 24, which makes it as 1, and instead of that I want here 352 by 112. So here I have s square, but here I want only s, so I have to multiply by divide by s. So which will give me 352 s by 112, and here if I am left with s square. So again, since it is positive, 24 s square by 352, I'll just multiply by 24 by 352, which will make my remainder as 0. So since this is done on impedance function, the first term is Z1, the second term becomes Y1, third term becomes Z2, the fourth term becomes Y2, and the last term becomes Z3. So since this is Z and this is an constant function, so it indicates R1 value is 3 by 8 ohms. Since this is admittance function, it is in the form of 1 by Ls. So L1 value is 64 by 14. So it is 14 by 64 henries. So again, this is also a constant in impedance. So R2 value is 1. If you simplify, it becomes 196 by 352 ohms. Here admittance, since it is admittance, is in the form of 1 by Ls. So it is L2 value is, if you simplify this, you will get 21 by 968 henries. And the last term is a constant, so R3 value is 24 by 352 ohms. So the network synthesis ladder, the first term is a resistor of value 3 by 8 ohms. 3 by 8 ohms. The second element is an inductor 14 by 64 henries. So second term is an inductor 14 by 64 henries. The third term is a resistor 196 by 352 ohms. The third term is 196 by 352 ohms. The fourth term is an inductor of 21 by 968 henries. 21 by 968 henries. And the last term is a resistor of 24 by 352 ohms. So this is the network after synthesizing the impedance function using our second form. So that was the procedure how to synthesize a given RL impedance function using 4 canonical forms. So in my next lecture, I'll give you a detailed procedure of how to synthesize a given RC impedance function using 4 canonical forms. Thank you.